It is the last day of November. Goodness gracious, the last day of November for 2017. November will come no more to our fair shores. Crud. Okay, we've been talking about this like you know what it means. So you better know what it means. Valence electrons. The electrons on the outermost occupied main energy level, they get given up, they get gained, they get shared. These form the basis of all chemical behavior because suddenly they are moving around, trading places, holding hands, swapping. This piece right here, looking at a group and knowing immediately how many valence electrons it has, you have to be good at that. You will be good at that. By the end of January, you're going to be at a point where I could wake you up at 2 in the morning from a dead sleep. Kendra, wake up. How many valence electrons does calcium have? And you would, before you even asked for coffee, mutter 2. That's how good you're going to be. I promise not to test this, but you're welcome to have chemistry slumber parties and test it on one another. Wake one another up at 2 in the morning. Quick! How many valence electrons does fluorine have? 7. You're going to be that good. You have to be that good. And my first year teaching chemistry, I didn't realize how good you had to be at that to do everything else that is totally foundational. And I let a few people slip through, and we got to March, and I had a couple people who couldn't do that, who couldn't just look at the periodic table and go, oh, that's got 3 valence electrons. And it made everything else horrible. It was a bad year. It was a rough year. I know that's foundational. I'm telling you that's foundational. I'm telling you you have to be that good at it. I'm telling you if you aren't that good at it, you need to work at it. If you realize, oh my God, I can't do that. You need to make a chemistry date. You need to come in for tutoring. You need to work on it because that is absolutely critical. In the S block, it's really easy because the group number is the number of electrons, the number of valence electrons. If you want to add that to your periodic table, you are more than welcome to. What that looks like is this, 1, 2. And you might want to put sometimes I put this valence electrons, which is just my own little symbol. Nobody else uses it. But you have to know that. So in the first 2 groups, it's super easy. In the transition metals, it's a little weird, and there's not a definite relationship. But once we get to the P block, it's really easy because it's the group number minus 10. So this is group 13. How many valence electrons do they have? 3. Group 14 has 4. Group 15, I'm going to run out of room here because I wrote too big. Group 15 has 5. Group 16 has 6. Group 17 has 7. You get the picture. Because knowing that immediately allows you to know immediately what type of ion they'll form or if they're more likely to share. If they're more likely to give up, gain, or share. So you have to know that just immediately. How many valence electrons does group 18 have? 8. And therefore, they tend to not gain or give up or share. They're totally satisfied. Okay. Electronegativity is something that we're going to introduce here. But in the next chapter, this is going to become a central idea in the next couple of chapters because electronegativity is all about how atoms behave when they are bonded. So, this is all about sharing. When we bond 2 atoms together, we said there's an electron cloud. So we've been drawing all those silly little Bohrian atoms with the little concentric racetracks with the little electrons buzzing around them. But we said that in reality, it's more like a big glob of cotton candy. That's the quantum model. And, there are sort of multiple blobs going in all directions. But we call that whole thing, I'll do this in green, the electron cloud. Yeah, it kind of looks like a flower. I like that. Totally not realistic, but I like it anyway. When we've got two atoms that are bonded, and I'm going to just copy this. When these two atoms are bonded, especially when they are sharing electrons, what we see is that these electron clouds kind of overlap. And this becomes sort of one big electron cloud. Okay? Well, atoms don't always share evenly. So if you have one atom that is basically more attracted to the electrons in the cloud, instead of this sort of even distribution of electrons, and I'll copy that there, what we tend to see is something that looks a little bit more, let me redraw this, looks a little bit more like that, where one atom is pulling the electron cloud over. Who here has ever had to share a bed with a cousin, sibling, best friend on a slumber party when you were, 8 years old? Have you had to share covers with somebody? Watching a movie on the couch and sharing a blanket. Does everyone share covers evenly? No. There are blanket hogs in this world, and we all know it. There are people who will execute the blanket death roll. That is where you grab the covers and roll until you've stripped them off the other person. It's a very effective maneuver, by the way, gotta say. My husband's a pro at it. That's kind of what a highly electronegative atom does. It blanket hogs, except the blanket we're talking about here is the electron cloud. It pulls the electron cloud until it's got way more of the electron cloud than the other atom. As we go across a period, so as we go, let's pick a, let's pick a period to examine. Let's think about this period, third period. Who in that period is holding on to their electrons most loosely? Who's got the biggest atomic radius? Who's got the lowest ionization energy? Who is most willing in that period to give up their electron? Put your finger on your periodic table on the atom in that period most willing to get rid of an electron. Get out your periodic table. Don't you dare sit down for this conversation without a periodic table out in front of you. Okay, everybody got their finger on sodium, I assume? Why? Biggest atomic radius in its period. Lowest ionization energy in its period. Very, very likely to be talked out of an electron. Doesn't take a whole lot to get an electron off of sodium. Who in this period would have the smallest atomic radius? The highest ionization energy. Who's the toughest? Yeah, and we're only looking all the way up to chlorine. We're not even going to talk about the noble gases. Chlorine. Who do you think is the biggest electron hog? Who's holding their electrons more tightly? Chlorine. Who's going to have the highest electronegativity? Chlorine. So as we go across a period, we tend to see increasing electronegativities. We also tend to see, and this trend is a little bit less well-defined. Electronegativity tends to be highest at the top of a group. And if you think about it, where is your smallest atomic radius in a group? Let's look at a group. Where's the smallest atomic radius in that group? Put your finger on it. Boron. Largest atomic radius, whatever the heck this is. Element 113. So as we go down, we tend to see decreasing electronegativities. Now, given all of that, let me clear all the strokes. On this entire periodic table, If you had to make a bet, and we're not counting the noble gases here, we don't talk about electronegativity. We don't talk about electronegativity with noble gases because they don't typically participate in bonding. And this is only when you're bonding. If you had to make a guess, put your finger on the element on that periodic table that you suspect would have the highest electronegativity of anything based on the two trends we just talked about. Fluorine is by definition the highest electronegativity of any element. It doesn't share very well. Perhaps you have a sibling who doesn't share very well, or you've had experience with someone in your life who didn't share very well. That's fluorine. Fluorine's an absolute pig about electrons. Okay, this is the last bit we have. In the D block, the properties of those elements are fairly consistent. So we've said, well, within this block, this varies, this varies, this varies. Within the D block, they're more or less consistent. They're all lustrous. They're all malleable. They're all ductile. They're all conductive. They all participate in the same kind of bonding. The way they share electrons is all the same. When they do vary, it's not real predictable. So the D block is the one where there really aren't understandable trends, at least not anything that we understand yet, where we can say, oh, well, this is why. So for instance, we've got the magnetic 3. We have 3 elements in the middle of the D block that are magnetic. Why aren't they all magnetic? Don't know. Why isn't gold magnetic? Don't know. Why isn't zinc magnetic? Don't know. Why iron, cobalt, and nickel? Don't know. But in the D block, it's a little bit less predictable. In general, they're pretty consistent. There are some variations, but we can't predict them based on any of these trend pieces of information. F block, same way, pretty consistent. When they do vary, you all hear the jet engine taking off. I think it's the heating system. It sounds like there's a jet taking off from the roof right now. It's not just you. It's not in your head. You're not going crazy. You might be going crazy, but that's not part of it. In the D and F block, the way they make ions is also a little bit less predictable. They don't consistently, like we can look at S block and say, oh, this always makes a +1, this always makes a +2. D and F block, we can't do that. So when we start to talk about ion formation and bonding in the next chapter, we're going to look at the fact, well, basically you're just going to get a chart and you're going to use it. You're not going to have to memorize those because you can't. There's no rhyme or reason to them. So that's all we have for this chapter. So when we come back after the 4 minutes, I'll give you a minute to get the homework together. If you are departing our happy shores, second period, stick your stuff in the box. Questions in general. How do you feel about recognizing those trends? I guess we already kind of covered that. So tomorrow we're going to go through some practice. You'll have a FIP quiz tomorrow on doing that. And then in the study hall, if people need help, we'll do some small group work. Test will be Monday. And then we're going to dive right into Chapter 6 as fast as we can. So, because Chapter 6 is bonding, and then Chapter 7 is compound naming. So, all right. That's it.